Tonight, most people who know anything about Andromeda know one number: 2.5 million light-years, the distance to the nearest large galaxy, the farthest object visible to the naked eye. A fact that appears in every astronomy book and every space documentary, stated with the quiet confidence of something fully understood. The number is correct, but it is also, in an important sense, only part of the measurement, because 2.5 million light-years is the distance to Andromeda's core, the bright central disk that cameras photograph easily and eyes can just barely detect on a clear night. What surrounds that core, the vast, faint, mostly invisible outer structure that constitutes the majority of the galaxy's physical extent, reaches considerably closer than the core does. When modern surveys finally mapped how far Andromeda's outer halo extends, the answer did not match the number most people carry. It was larger, significantly larger. Large enough that the standard quoted distance understates the galaxy's true presence in the local universe by a meaningful amount. That is what this video is about. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. On a clear, moonless autumn night, in the northern hemisphere, there is a galaxy you can find with nothing more than your eyes. It sits in the constellation Andromeda, part of a distinctive pattern of stars that sweeps across the sky in a long curved line. If you trace that line carefully and the sky is dark enough and your eyes have had time to adjust to the darkness, you will find a faint, elongated smudge. Not a point of light like a star. Something softer, something with a slight extension, a barely perceptible oval shape that seems to glow at its centre and fade at its edges. That is Andromeda. Most people who find it for the first time feel a quiet kind of awe. The awareness that they are looking at an object so far away that the light arriving at their eye left its source before modern humans had yet appeared on Earth. The awareness that what they are seeing is not a star, not a planet, not any object within our own galaxy, but an entire separate galaxy containing hundreds of billions of stars, sitting at a distance of roughly 2.5 million light-years. The feeling is accurate. The picture behind it is not quite complete, because what the naked eye detects when it finds that faint smudge is not the full galaxy. It is the core. The dense, bright, central region where the stars pack tightly enough that their combined light registers to a human eye across 2.5 million light-years of space. The outer galaxy, the parts that extend beyond that core in every direction, are simply too faint for the eye to pick up at this distance. They are there. They are real. They contain stars, stellar streams, vast quantities of older stellar populations scattered across enormous volumes of space. But the eye, without assistance, cannot reach them. And here is where the picture begins to shift. Because the outer galaxy is not a thin, negligible fringe around the bright centre. It is the majority of the galaxy's physical extent. The smudge visible to the naked eye corresponds roughly to the innermost disk of Andromeda, the region astronomers call the optical disk. Beyond that disk, the galaxy continues outward into a structure called the stellar halo, a diffuse spherical distribution of older stars surrounding the main body of the galaxy like an enormous faint cloud. The full extent of that halo, as surveys have measured it, is the number that rewrites the standard picture. But before that number can land with its proper weight, there is an intermediate step worth taking. The visible disk itself, the part that shows up in long exposure photographs, is already larger than most people imagine. That is where the actual scale begins to open. When a telescope points at Andromeda and a camera takes a long exposure, the image that results is the one most people have seen. A bright oval core, glowing intensely at the centre. A disk of spiral structure extending outward from that core, tilted at an angle so that it appears elongated rather than circular. Lanes of dark dust tracing through the disk, marking the regions where cold gas and dust absorb the light of stars behind them. The whole structure surrounded by a gradually fading glow that dissolves at the edges of the frame. That image is accurate. But it has a built-in limitation that the photograph does not announce. The edge of a galaxy in a photograph is not the edge of the galaxy. It is the edge of what the camera's sensitivity can detect. Stars and gas at the galaxy's outer limits are not absent from the image because they are absent from the galaxy. They are absent from the image because they are too faint to register. Every photograph of a galaxy shows you the brightest portion of the structure. The rest is outside the frame, not because the telescope did not look far enough, but because what is out there does not produce enough light to cross the detection threshold of the instrument being used. This matters for Andromeda because the visible disk, as captured in standard telescope photography, is already a structure of considerable size. Andromeda's disk spans roughly 220,000 light-years in diameter. That number deserves a moment. The Milky Way's disk is estimated at roughly 100,000 to 120,000 light-years across. Andromeda's visible disk, the part that fits inside a standard telescope image, is already approximately twice the diameter of our own galaxy's disk. It contains, by current estimates, somewhere on the order of 1 trillion stars. Arranged across 220,000 light-years of space, gravitationally organised into spiral arms, supported by a dense central bulge of older stars and threaded throughout with cold gas clouds where new stars continue to form. The disk alone is a system that dwarfs the Milky Way's visible structure in pure diameter, and the disk is only the beginning. The photograph's edge is not where Andromeda ends. It is where the photograph stops being able to see Andromeda. Beyond that edge, the galaxy continues outward into regions that standard photography cannot reach, into a structure that requires specialized surveys, long integration times, and instruments specifically designed to detect extremely faint, diffuse light. The disk you see in the image is the lit interior of something considerably larger. And surrounding it, invisible in any casual observation, is a structure that changes the scale conversation entirely. Every large galaxy has one. Not a disk, not a ring, not a spiral arm, but a third major component. One that receives considerably less attention in popular astronomy than the spectacular spiral structure or the luminous central bulge. It is called the stellar halo, and understanding what it is, why it forms, and how large it grows is the key to understanding why Andromeda's true scale is so different from the number most people know. The simplest description of a stellar halo is this: it is the roughly spherical distribution of stars surrounding a galaxy's disk. Not the flat, organised, rotationally symmetric population of the disk itself, but a diffuse, scattered population of older stars that extends outward in every direction from the galaxy's centre, like an enormous faint fog surrounding the bright city lights of the main structure. Think of a large city seen from above at night. The city centre is bright, dense, unmistakable. The organised streets and neighbourhoods extend outward from that centre in patterns that reflect planning and structure. But beyond the clear boundary of the city, the light does not simply stop. It fades gradually into a softer glow, a diffuse spread of suburban light that extends much further than the city's official limits, thinning as it goes until it eventually dissolves into darkness. The city's official boundary is one measurement. The full extent of its light is a considerably larger one. A stellar halo is something like that outer glow, except the scale involved is measured in hundreds of thousands of light years, and the stars that make up the halo are not recent additions. They are among the oldest stars the galaxy contains. The halo forms through two main processes. The first is primordial, when a large galaxy is young and still assembling itself from the collapse of a massive gas cloud. The very first generations of stars form quickly and chaotically, some of them ending up in the extended, roughly spherical distribution that becomes the halo. These stars are old, metal-poor, and orbit the galaxy's centre in eccentric paths that take them far from the disk plane. The second process is ongoing. When smaller galaxies venture too close, Andromeda's gravity pulls them apart. The stars stripped from these smaller galaxies disperse into the halo, adding new stellar populations to the already existing structure. The result is a component of the galaxy that is dramatically larger than the visible disk. Extremely faint, because its stars are spread across such an enormous volume of space, and largely invisible in standard observations, because no individual patch of it is bright enough to stand out clearly. The Milky Way has its own stellar halo. It extends somewhere between 300,000 and 650,000 light-years from our galaxy's centre, though the exact boundary depends on how sensitive the survey used to measure it is. As surveys improve, the estimated extent tends to grow. If the Milky Way's halo is already that large, Andromeda's, belonging to a galaxy that is more massive and has had a richer history of absorbing smaller galaxies, would be expected to extend even further. The question was how far. The answer came from a survey that was designed from the beginning to look where other surveys had not looked carefully enough. Its name is the Pan-Andromeda Archaeological Survey, abbreviated to PANDAS. It used the Canada-France-Hawaii telescope, a large optical instrument situated on the summit of Mauna Kea in Hawaii, to conduct a systematic, multi-year imaging campaign covering an enormous area of sky around Andromeda. Not a quick snapshot, not a survey designed to capture the galaxy's bright regions. A deep, patient, methodical mapping program specifically intended to detect the faintest stellar populations at the greatest distances from Andromeda's centre. The technique relied on identifying individual red giant stars in Andromeda's outer halo. Red giants are stars in a late stage of their lives, temporarily much larger and brighter than they were on the main sequence, bright enough that they can be detected individually even at Andromeda's distance if the survey goes deep enough. By finding these stars, measuring their distances, and mapping their positions across the sky, the survey could build a picture of how far Andromeda's stellar population extended. The survey covered roughly 400 square degrees of sky around Andromeda. To give a sense of scale, the full moon covers approximately half a square degree. 400 square degrees is the equivalent of mapping a patch of sky containing roughly 800 full moons. This was not a small sample. What the survey found changed the number. Andromeda's stellar halo was detected extending at least 1.3 million light-years from the galaxy's centre, not the 220,000 light-year diameter of the visible disk. Not a modest outer envelope a few tens of thousands of light-years deep. A radius of 1.3 million light-years, meaning the full diameter of the halo from one edge to the other, if measured straight through the galaxy's centre, spans roughly 2.6 million light-years. Sit with that number alongside the other one. The distance from Earth to Andromeda's core is approximately 2.537 million light-years. The diameter of Andromeda's full halo, from edge to edge, is approximately 2.6 million light-years. The galaxy is, in terms of its measured stellar extent, approximately as wide as it is far. The distance from the Milky Way to the centre of Andromeda is barely larger than Andromeda itself. This is not a minor adjustment to the standard picture. It is a fundamental change in what Andromeda means as a physical object in the local universe. The outer halo of Andromeda is not a featureless fog. That was one of the most important findings to emerge from the detailed surveys of Andromeda's outer structure. What those surveys found was not just a smooth, gradually fading distribution of old stars. They found structure. Streams of stars organized into long, coherent arcs. Overdensities in some regions and relative voids in others. Evidence, written in the positions and motions of stars across hundreds of thousands of light years, of a long history of gravitational encounters. The most prominent of these structures is something called the Giant Stellar Stream. It was first identified in 2001, before PANDAS had begun its comprehensive mapping, by a team of astronomers studying Andromeda's outer regions. The stream is an arc of stars stretching to roughly 820,000 light-years from Andromeda's centre, curving around the galaxy's outer halo in a path that traces the orbit of something that once existed and no longer does. That something was most likely a smaller galaxy, a dwarf galaxy possibly comparable in size to the Large Magellanic Cloud, one of the Milky Way's own satellite companions. At some point in the past, this galaxy wandered too close to Andromeda. Andromeda's gravity began to pull harder on the near side of the approaching galaxy than on the far side. This differential pull is called a tidal force, and over time it stretched the smaller galaxy into an elongated shape, then pulled it apart entirely. The stars that had been bound together in a single structure for billions of years were separated, scattered along the orbit of their former home, stretched into a stream that traces the path their galaxy travelled as it was consumed. Those stars did not disappear. They became part of Andromeda's halo, and their arrangement, organised into a stream rather than randomly scattered, persists for billions of years because stars in a stream all share roughly the same orbital energy and continue to move together through space long after the galaxy that contained them is gone. The Giant Stellar Stream is one of the largest coherent structures in the local group of galaxies, at 820,000 light-years from Andromeda's centre. It already extends further from Andromeda than the Milky Way's disk is wide. And it is one of several such structures. PANDAS and subsequent surveys identified multiple other streams, shells, and stellar overdensities in Andromeda's outer halo, each one a record of a smaller galaxy that came too close and was absorbed. The halo is not just large, it is a graveyard. Every stream in Andromeda's outer structure is the aftermath of a merger, the stellar remnant of a galaxy that no longer exists as a distinct object. Andromeda has been doing this for billions of years, drawing in smaller companions, stripping them of their stars, adding those stars to its outer structure. The halo's current extent is, in part, a record of every galaxy Andromeda has consumed, and around Andromeda there are still galaxies it has not yet consumed. Andromeda does not travel alone. Around it, in orbits that range from a few 100,000 to roughly 1 million light-years in radius, are more than 30 confirmed satellite galaxies. Some are large enough to be visible in binoculars, most are small. Faint dwarf galaxies that would be entirely invisible without a telescope. Together they form a system of companions that surrounds Andromeda and maps, through their positions and the fact of their gravitational binding, the full extent of the gravitational territory Andromeda commands. The two most prominent satellites are M32 and M110, sometimes visible as small oval smudges near Andromeda's disk in long-exposure photographs. M32 is a compact elliptical galaxy, unusually dense, its stars packed closely together in a structure that has survived close passages near Andromeda's disk. M110 is a larger, more diffuse dwarf elliptical, orbiting at a somewhat greater distance. Both sit relatively close to Andromeda's main body, within a few 100,000 light-years. But the satellite system does not end with the obvious companions. Surveys of the space around Andromeda have identified numerous dwarf satellite galaxies scattered across much larger distances. Some of these satellites orbit at distances approaching 800,000 light-years from Andromeda's centre. The fact that they remain gravitationally bound to Andromeda at that distance is not incidental. It tells us something directly about the mass distribution of the full system. For a satellite to remain in orbit at 800,000 light-years rather than escaping into the general intergalactic medium, there must be enough mass inside that orbit to hold it. The satellite's position is, in effect, a measurement of Andromeda's gravitational reach. By this measure, the full gravitational system Andromeda commands, including its dark matter halo, which will be addressed shortly, extends to at least 1 million light-years, and by some estimates considerably further. This is the territory Andromeda governs. Not the 220,000 light-year disk, not even the 3 million light-year stellar halo. The full system, traced by the orbital distances of its most distant satellites, spans a volume of space that is large even by the standards of this already large galaxy. And the Milky Way's own system is not separate from this. The Milky Way has its own satellites. The large and small Magellanic Clouds are the most prominent, visible from the southern hemisphere as detached patches of the Milky Way's light. The Milky Way has roughly 12 to 30 satellite galaxies, depending on how faint the survey goes, comparable in number to Andromeda's system. Several of these satellites orbit at distances of 200,000 to 400,000 light-years from the Milky Way's centre. The two satellite systems, Andromeda's and the Milky Way's, are not a combined million light-years apart. They are beginning to occupy the same general region of local space. The question of where Andromeda's gravitational territory ends and the Milky Way's begins is not a question with a clean answer. At the outer limits of both systems, the boundary is not a line. It is a gradual transition through shared space. 2.5 million light-years, that is the gap to Andromeda's core. 1.3 million light-years. That is how far Andromeda's stellar halo extends from its centre. Place both numbers on a line. The far edge of Andromeda's halo is 2.537 million light-years from Earth. The near edge of Andromeda's halo, the side facing the Milky Way, sits at 2.537 minus 1.3 million, which is approximately 1.2 million light-years from Earth. The Milky Way's own stellar halo, depending on the survey and the detection threshold used, extends somewhere between 300,000 and 650,000 light-years from our galaxy's centre. Add the two halo extents together, 1.3 million plus roughly 0. 65 million equals approximately 1.95 million light-years of combined halo structure. The gap between the two galaxies is 2.537 million light-years. The combined extent of the two halos is approximately 1.95 million light-years. The arithmetic points toward a gap of perhaps 600,000 light-years or less between the outer edges of the two halos, depending on which measurements are used. Some research suggests the halos may already be in contact or near contact at their outermost, most diffuse limits. This requires care in how it is stated. The outer regions of both halos are extremely tenuous. The density of stars in the outermost halo is extraordinarily low, far lower than in the disk or even the inner halo. The contact being described here is not a collision of dense structures. It is the meeting, or near meeting, of very faint, very sparse populations of stars at the furthest edges of both systems. No observer inside either galaxy would perceive anything dramatic from this. but as a statement of physical scale, it is meaningful. The two largest galaxies in the local universe are separated by a gap that at their outer limits has narrowed to something comparable to the diameter of the Milky Way's visible disk. The standard image of two clearly separate galaxies sitting safely apart from each other at 2.5 million light-years does not fully represent the physical situation. The distance to Andromeda's core is 2.5 million light-years. The distance to Andromeda's near edge is considerably less. These are not the same measurement, and the difference between them is the entire point of the title. Most people, when they hear about the Andromeda collision, picture something catastrophic. Two galaxies slamming together, stars colliding, planets destroyed, a cosmic disaster arriving in a few billion years with the force of two enormous structures hitting each other at speed. The reality is stranger, slower, and in its own way more disorienting than the collision picture suggests. The cores of Andromeda and the Milky Way are currently approaching each other at roughly 110 kilometers per second relative to the distance between them. At that speed, the first close pass of the two galactic cores is estimated to occur in roughly 4 to 5 billion years. This is a long time by any human standard, but it is also a well-supported prediction based on precise measurements of Andromeda's motion relative to the Milky Way, including data from the Hubble Space Telescope that measured not just Andromeda's approach velocity, but also its sideways motion, confirming a nearly head-on trajectory. When the encounter occurs, it will not look like what the word collision suggests. The reason is the same reason that makes interstellar space feel so empty. Stars are not packed closely together. In the Milky Way, the average distance between neighbouring stars is several light-years. If every star in the galaxy were reduced to the size of a grain of sand, the nearest neighbouring grain would be roughly 300 kilometres away. When two such sparse systems overlap, the probability of any individual grain, any individual star, directly hitting another is extremely small. Stellar collisions during a galaxy merger are not impossible, but they are rare. The violence of the encounter is not physical impact. It is gravitational. What happens when two galaxies pass through each other is that the gravitational landscape of both is disrupted. Stars that had stable orbits in their home galaxy find those orbits perturbed by the gravity of the passing system. Some are flung outward into new trajectories, others are pulled inward. Spiral arms are stretched and distorted. Gas clouds in both galaxies are compressed by the encounter, potentially triggering bursts of new star formation in the disturbed regions. After the first pass, the two galactic cores will separate again before being pulled back by their mutual gravity for a second pass. Then a third. Over billions of years, the two systems will spiral together, their structures gradually merging into a single new galaxy. The final product will not be a spiral. It will most likely be an elliptical galaxy, a large, roughly spherical concentration of stars without the organized disk structure that both current galaxies possess. Astronomers have already given this future galaxy a name. Milkomeda, or in some references, Milkdromeda, a merged structure containing the combined stars of both galaxies, orbiting a new combined center of mass, moving through the local universe as a single object. But the point for this particular conversation is not the details of the merger's phases or the fate of the solar system within it. The point is simpler. The merger process has a beginning. And that beginning is not 4 billion years in the future. The outermost structures of the two galaxies are already in the same general region of local space. What will happen in 4 billion years is not the start of contact. It is a much later chapter in a process that has already begun at the outer limits. There is a structure that surrounds and governs the whole of the local group. and within it Andromeda holds a specific position. The local group is the name given to the collection of galaxies that are gravitationally bound to the Milky Way and Andromeda. It is not a cluster in the way that larger galaxy clusters are clusters, with hundreds or thousands of members packed together. It is a small, loose association of roughly 60 to 80 galaxies, most of them dwarfs, all of them bound together within a region of space roughly 10 million light-years across. Within this group, two galaxies dominate. Andromeda and the Milky Way account for the vast majority of the group's total stellar mass. Every other member is significantly smaller. The Triangulum galaxy, M33, sometimes listed as the third largest member, contains perhaps 30 to 40 billion stars. Andromeda, with roughly 1 trillion, is 25 to 30 times more massive than M33. The Milky Way is somewhere between Andromeda and M33 in mass, with most current estimates placing the Milky Way at slightly less massive than Andromeda, though the comparison involves significant uncertainties. All the dwarf galaxies in the local group orbit around the gravitational centre of mass of the whole system, which lies somewhere between the Milky Way and Andromeda. Several of the group's dwarfs are more properly understood as satellites of one of the two large galaxies rather than independent members. M33 itself is most likely gravitationally associated with Andromeda rather than being a free-floating member of the group. Andromeda is not simply one of many similar galaxies in the neighbourhood. It is the most massive individual galaxy in the immediate cosmic neighbourhood, the dominant mass around which the outer structure of the local group is partly organised, and the object whose gravity has been shaping the trajectories of nearby galaxies for billions of years. The Milky Way is large. By most current estimates, Andromeda is larger. And the two of them, falling toward each other's combined centre of mass, are the gravitational anchors of everything within 10 million light-years. There is a version of Andromeda that most people never see, and it is not because it does not exist. It is because the instruments most commonly pointed at galaxies are not designed to see it. Standard optical telescopes, the kind that produce the classic long-exposure photographs of spiral structure and glowing central bulges, are optimized for detecting the bright, organized, high-surface brightness features of galaxies. They are excellent at showing spiral arms, dust lanes, star-forming regions, and the dense stellar populations of galactic disks. They are not well suited to detecting the extremely faint diffuse structures at the outer limits of galaxy halos, and they are not the only way to observe a galaxy. Different wavelengths of light reveal different components of the same object. Infrared observations, sensitive to cooler stars and thermal emission from dust, show Andromeda's disk extending further than optical surveys do and reveal the distribution of its older stellar populations in different proportions than visible light imaging. Infrared observations are also less affected by dust absorption, meaning structures hidden behind dust lanes in optical images become accessible. The infrared Andromeda is a somewhat larger, somewhat differently structured version of the optical Andromeda. Ultraviolet observations trace the distribution of young, hot, massive stars, the kind that form in the densest parts of the disk and in star-forming regions. These stars are short-lived, and their presence marks where active star formation is occurring. The ultraviolet Andromeda reveals the current loci of stellar birth, the regions of the disk where the galaxy is still producing new stars from its gas reservoirs. Radio observations, particularly those targeting the emission from neutral hydrogen gas at a wavelength of 21 centimeters, trace the galaxy's gas reservoir far beyond its stellar disk. Neutral hydrogen is the raw material from which stars form, and it is distributed throughout the disk and beyond. Radio surveys of Andromeda have detected neutral hydrogen extending to distances considerably larger than the optical disk. in some directions pushing toward 300,000 to 400,000 light-years from the galaxy's center. The gas reservoir of Andromeda is physically larger than its stellar disk. X-ray observations, sensitive to hot plasma at temperatures of millions of degrees, reveal the gas in Andromeda's circumgalactic medium, the hot diffuse material filling the space around and above the disk. This hot gas component extends into the halo, filling volume between the discrete stars of the stellar halo with a tenuous high-temperature plasma. Every wavelength that astronomers have pointed at Andromeda has revealed a layer of the galaxy extending beyond the previous one. The optical disk gives way to the infrared disk, which gives way to the radio-traced gas reservoir, which gives way to the stellar halo detected by deep optical surveys, which is surrounded by hot circumgalactic gas detected in X-rays, which is itself surrounded by the dark matter halo that can only be traced through gravitational inference. Each layer is real. Each one is part of what Andromeda is. The photograph most people know shows one of these layers. The full galaxy is the sum of all of them, and the sum is considerably larger than any single image suggests. Every time a new observational technique has been applied to Andromeda, the galaxy has grown in our measurement. Not because the galaxy is changing, because the instrument used to measure it keeps getting better at detecting what was already there. The full gravitational boundary of Andromeda extends further than even its stellar halo suggests. The stellar halo, the structure detected by PANDAS and subsequent surveys at 1.3 million light-years, is made of stars. Stars emit light. Stars can be detected at Andromeda's distance if a survey is sensitive enough and covers a wide enough area of sky. But a galaxy is not just its stars. The majority of a large galaxy's mass is not in stars at all. It is in something that does not emit light, does not absorb light, and cannot be detected by any direct observation with any current instrument. Dark matter. The name is a description of its observational property rather than its physical nature. It is matter, meaning it has mass and therefore gravitational influence, but it is dark, meaning it does not interact with electromagnetic radiation in any detectable way. It does not glow, it does not reflect, it does not absorb, it only makes its presence known through gravity. The evidence for dark matter in galaxies comes primarily from rotation curves. As a galaxy rotates, stars at different distances from the center orbit at different speeds. In a simple system where all the mass is concentrated near the center, stars further from the center should orbit more slowly, the same way the outer planets of the solar system orbit more slowly than the inner ones. But observations of Andromeda and every other large galaxy show that stars in the outer disk do not slow down as expected. They maintain roughly constant orbital speeds far from the center, well beyond the region where visible stars and gas can account for the gravitational pull required to keep them in orbit. The only explanation consistent with observations is that there is mass in the outer regions that is not visible. That mass is distributed in a roughly spherical halo extending far beyond the stellar disk and even beyond the stellar halo. It is what holds the galaxy together as a single gravitational system. For Andromeda, current models of the dark matter halo suggest it extends to approximately 2 million light-years from the galaxy's center. This estimate comes from modeling the mass distribution required to explain the orbital dynamics of the galaxy's outer stars, its satellite galaxies, and the dynamics of the local group as a whole. It carries significant uncertainty because dark matter cannot be directly imaged, and its distribution can only be inferred from gravitational effects. But even with that uncertainty, the implication is clear. The distance from Earth to Andromeda's center is 2.537 million light-years. The estimated extent of Andromeda's dark matter halo is approximately 2 million light-years. The gap between Andromeda's gravitational edge and the Milky Way's centre, by this measure, is roughly 500,000 light-years. Not much larger than the distance from the Sun to the Milky Way's own centre, roughly 26,000 light-years, multiplied by about 20. The gravitational reach of Andromeda extends roughly 80% of the way to the Milky Way's centre. The separation between the two galaxies is real, but the word separation implies a cleaner gap than the physics justifies. The dark matter halos of the two galaxies, the true gravitational extent of each system, are already occupying the same general region of space. The number most people carry for Andromeda is accurate. 2.5 million light-years to the core. But now there are other numbers on the table. The stellar halo extends 1.3 million light-years from Andromeda's centre. That places Andromeda's near-stellar edge approximately 1.2 million light-years from the Milky Way. The dark matter halo extends an estimated 2 million light-years from the centre, placing its gravitational edge approximately 500,000 light-years from the Milky Way. The most distant satellite galaxies orbit at distances approaching 1 million light-years from Andromeda's centre, some of them already closer to the Milky Way than they are to Andromeda's core. The standard number describes one thing: the gap between our galaxy's centre and Andromeda's centre. It does not describe the gap between the two galaxies as physical systems. That gap is smaller. Measured by stellar extent, it is roughly 1.2 million light-years. Measured by gravitational reach, it may be as small as several 100,000 light-years. Measured by the overlap of the most diffuse outer halo populations, it may already be zero, though with significant uncertainty about whether any overlap constitutes meaningful physical contact, given how tenuous those populations are. The difference between the core-to-core distance and the edge-to-edge distance is the difference between knowing where the centre of a city is and knowing where the city ends. A city's centre and a city's edge are not the same point. Andromeda's centre and Andromeda's edge are not the same distance from Earth. 2.5 million light-years puts Andromeda at a comfortable remove. The full-scale picture, with stellar halo and gravitational reach included, puts parts of Andromeda much closer than that number suggests. Not close in any human sense. Not close in any sense that changes the night sky visibly or creates any physical consequence for Earth. But close in the sense that the scale of Andromeda as a system is not captured by the distance to its core. The title said the scale is bigger than most people think. The accumulated measurements confirm it. Every layer of the galaxy, optical disk, stellar halo, tidal streams, satellite system, dark matter envelope is larger than the layer before it, and the outermost layers reach into territory that the core-to-core distance does not reflect. The autumn sky looks the same tonight as it did 1,000 years ago. The smudge of Andromeda appears in the same position, at the same brightness, occupying the same unremarkable patch of sky in the constellation that shares its name. To any observer without a calculator and a database of precise measurements, nothing has changed. Nothing appears to be in motion. But Andromeda is approaching. At roughly 110 kilometers per second, the core of Andromeda is drawing closer to the Milky Way. That speed sounds significant until you convert it to the units of the distances involved. At 110 kilometers per second, Andromeda's core closes roughly 3.5 billion kilometers on the Milky Way every year. Against a separation of 2.537 million light-years, that annual closing distance represents a fraction so small it would take scientific notation to write it usefully. The motion is real. It is simply operating on timescales that dwarf anything in human experience. 1 billion years ago, Andromeda's core was further away than it is tonight. The stellar halo, which now extends within roughly 1.2 million light-years of the Milky Way, was not yet that close. The outer limits of the two galaxy systems were further apart. The universe was measurably different at its local scale. 1 billion years from now, Andromeda will be closer. The smudge in the sky will be brighter, though not dramatically so from a human perspective in a single lifetime. In a few billion years, Andromeda will begin to be visible as something more than a smudge. Its disk structure will start to resolve against the background sky. In 3 billion years or so, Andromeda will be large enough in the sky that its spiral structure will be distinguishable without a telescope on a dark night, occupying a region of the sky many times the width of the full moon. In 4 to 5 billion years, as the two cores begin their first close pass, the night sky will contain a second galactic structure, filling a large portion of the visible sky, bright with the light of hundreds of billions of stars and the new star formation triggered by the encounter. The Milky Way's band, already a feature of our current sky, will be joined by Andromeda's approaching structure. The sky will change in a way it has not changed in billions of years. All of this is a continuation of something already in progress. The approach is not a future event that begins at some point. It is an ongoing condition of the local universe, currently producing the situation where Andromeda's outer halo is within roughly 2 million light-years of Earth, with the dark matter halos of both galaxies are already likely occupying overlapping volumes of space, where the boundary between the two galaxy systems is less a clean line and more a gradual transition through shared gravitational territory. Tonight's sky is a single frame in this sequence, a moment when the two largest galaxies in the local universe are close enough that one is visible to the naked eye of observers on a planet inside the other, but still far enough apart that the encounter exists only in mathematics and long baseline telescope measurements rather than in anything the unaided eye can detect. That will not always be true. The sky is already in motion. The motion is simply too slow for any individual life to perceive. Go outside on a clear autumn night and find the smudge. It is faint. It requires dark skies and a moment of patience for the eyes to adjust. It sits in a specific part of the constellation Andromeda, just off the line of stars that marks the constellation's shape. Most people who find it feel the same quiet recognition that they are looking at something genuinely far away, something outside the Milky Way, something that takes the mind a moment to fully accept. That feeling is correct. And it is also incomplete. The smudge is the core of a galaxy whose stellar halo extends 1.3 million light-years from its center. It is the bright center of a system whose gravitational reach extends an estimated 2 million light-years outward. It is the most visible part of a structure that has consumed dozens of smaller galaxies throughout its history, leaving their stars scattered in streams and shells across hundreds of thousands of light-years of its outer halo. It is the gravitational anchor of a system of more than 30 satellite galaxies, some of them orbiting at distances comparable to the gap between the two galaxy cores. The number most people know, 2.5 million light-years, is accurate. It describes the distance to the center of the structure the eye is detecting. But Andromeda does not begin at its center. It ends there, in the sense that the center is the far end of the galaxy's near side. The near end is much closer. The stellar halo's near edge sits roughly 1.2 million light-years from Earth. The dark matter halo's near edge may be as close as a few 100,000 light-years, closer than many of Andromeda's own satellite galaxies. The smudge is not a small, distant dot. It is the most distant, most luminous point of a system that is considerably more present in the local universe than the standard quoted distance suggests. When you look at the smudge, you are looking at the far end of Andromeda. The near end is already inside the space between it and you. This is what it means for the scale to be bigger than most people think. Not that the galaxy is farther away, it is exactly as far as the number says, to its centre. But it is also much closer than that number implies, at its outer limits. The true scale of Andromeda is not a single distance. It is the full range from core to outermost halo, from the bright centre that the eye detects to the diffuse outer edges that only specialised surveys can reach. That range is large enough to change the picture from a distant, compact object to a system whose gravitational and stellar presence already overlaps with the space the Milky Way inhabits. The smudge in the autumn sky is, in terms of physical scale, the tip of something much larger than it appears. The rest of it surrounds you, faint and invisible, stretching from that distant bright point across more than 1 million light-years of space toward where you are standing right now. Good night.